Hello class, hope you're doing well today. Today we're going to continue on our discussion of the nature of science to explore how we do science. So let's get started. So as we talk about how we do science, one of the major ways that we do science is descriptive science. So we're describing the world around us. And this is oftentimes the type of science that students forget about. So when we build a submersible that we send to the depths of the ocean that we've never been to before, and we describe the life forms that we see there, that is indeed science, and that is descriptive science. Or maybe we build a better telescope that allows us to see deeper into space than we've ever seen before. That is descriptive science. Or maybe we build a rover that we send to Mars or other extraplanetary bodies and describe what we see. That is descriptive science. So keep in mind, descriptive science is a very important aspect of science and should not be forgotten. Hint, hint. The other type of science that we do is hypothesis-driven science. This is also referred to as experimental science. This is the type of science that we probably think about more when we think about science. This type of science is generally guided by the scientific method. Now, when we hopefully you're familiar with the scientific method. I hope that you've been exposed to this at some point in your education so far. I want you to realize that the scientific method is not a rigid guideline. Okay, this is a general concept on how we do experimental science. One of the really cool aspects of the scientific method is that we humans, we innately use this to learn about the world around us. Not only have you been using this since you were a toddler, but you probably use the scientific method on a daily basis. So as we look at the scientific method, we start off with some observation. So maybe I go out to my car, put the key into the ignition, turn the ignition, and the car does not start. I've got an observation. My car just did not start. This is then going to raise one or more questions eventually. I might have some cursing. I might debate whether maybe I should just cancel the day because this is some bad omen or whatnot, or maybe I'm panicking on how the heck do I get into class or whatnot. Ultimately, I'm probably going to come back to the question, why did my car not start? So that observation will raise questions. In response to that question, we're going to propose one or more hypotheses. So we'll come and talk about hypotheses in just a little bit here, but these are proposed explanations for an observation. So some of those hypotheses might be things such as maybe the battery is dead, or maybe a squirrel got in and ate chewed on some of the wires in my car since it's been sitting in the garage for quite a while here. Maybe it's out of gas, what have you. Maybe the starter's broken. So these are hypotheses that we can have. In response to these hypotheses, we'll then carry out our experimentation. All right. So if my hypothesis is that the battery was dead, maybe I would try to jumpstart my car to see if that worked. So maybe it was the battery was dead. For me, in order to test whether the wires were chewed on or if it was the starter, I'd probably need a little bit more expert help. But those certainly would be things that we'd want to do. In the end, we'd then draw conclusions. So if I then try to jumpstart my car and that doesn't help at all, maybe I would tend to reject the hypothesis that the battery is the problem. Now, keep in mind we don't always follow strictly those steps in the scientific method. Those are a general guideline in science. Now, if I were to ask you initially, what is a hypothesis, you probably would have said an educated guess, or at least it would have gone through your mind that it's an educated guess, because this is how a hypothesis has typically been explained through grade school. What I'm going to ask you to do now is to set that idea aside, because we need a little bit more sophisticated understanding of what a hypothesis is. So let's take a look at a hypothesis with a little bit more sophisticated lens. So a hypothesis is a proposed explanation for an observation with a couple of guidelines behind it. First off, it must be testable. So that's a very important aspect that we need to keep in mind. When we propose a hypothesis, it must be within the realm of nature, and it must indeed be testable. So, for example, if my neighbor Jimmy comes over and sees that my car's not starting, and he says, well, it's probably a ghost, turning your engine off, not allowing it to start. It looks like you've got a ghost in your house too. That's not testable. We can't test a ghost. Or, maybe he's proposing that, maybe God just wants you to take the day off. Okay? That's not testable. We can't test God. And, if we take a look through literature in the past, most literature suggests that even if we could test a God, that's generally not a good idea. So a God or divine entity, by definition, is supernatural, thus beyond the natural world, and thus science can say nothing about that. It's not testable. It's not really within what we consider this narrow realm of science. Along those lines, we often we'll come back to that in a bit here. Another second aspect of a hypothesis is that it must also be falsifiable. So in terms of falsifiable, the idea is that there must be a chance that we could reject it. Okay? So a divine entity, the God or gods causing my car not to start, we can't reject that idea. Okay? A ghost, we can't reject that idea. We can't disprove that ghosts exist. All right? We can't explore the entire universe to see if there are any ghosts within the entire universe. Thus, we cannot disprove ghosts, or the idea of ghosts, if one should choose to accept them. So this is a very important idea within science, that things must be falsifiable. There must be a chance that it could be shown to be incorrect. Also, hypotheses cannot be proven with absolute certainty. Now, when we use the word proven, what we mean is that we are 100% certain, okay, that it is true. Keep in mind, one of our central tenets that we talked about previously is that all of our conclusions in science are tentative. That means they're subject to change. So we would never say that we have proven our hypothesis true, or that we've proven our hypothesis to be wrong. And in fact, if there's one word that really strikes a chord in this class, that is the 6-letter word proven, that we should not use that, all right? Because again, we do not have this 100% certainty, okay? If we test a hypothesis and it is not rejected, we would say that it is supported. So as we do science, let's take a look at this flow chart of the scientific method. We start off with some observation. So again, my car didn't start, raises a question. Why didn't it start? We propose multiple hypotheses. So maybe it's the battery, maybe it's the starter, maybe it's the ignition wires. Maybe somebody came in and took the engine out overnight. I don't know that. That's a hypothesis. And I don't know what hypothesis 5, maybe we're out of gas, right? So then we perform an experiment. So maybe I simply replace the battery, okay? If my car does not start after I replace the battery, I can reject that hypothesis. That leaves several hypotheses left. You know, maybe that it's the wires, ignition wires. Maybe it's the case that there's no gas. So again, I would perform a second experiment. And when we do an experiment, our goal ultimately is to reject some of these hypotheses. And in fact, as we look at the truest form of science, our ultimate goal is really to reject or falsify ideas. We end up with one remaining hypothesis that we accept. Okay? We might even test that hypothesis multiple times, and if it is supported, that would tend to confirm the hypothesis. But does that prove that that hypothesis is absolutely true? Well, it doesn't, because there could be another hypothesis which, when tested, also would be supported. Okay, so maybe we come down to the point where we're thinking it's gas, that we don't have any gas, but maybe it's not that we're out of gas, maybe that our fuel line was cut. In which case we'd really come up with fairly similar type results for some of these experiments. If our hypothesis fails, then we come back and we have to come up with new hypotheses. And then we perform more experiments. Again, our goal is to reject hypotheses. So when we do an experiment, again, the idea of an experiment is to test one or more hypotheses. One of the things we need to keep in mind are variables. So a variable is any factor that could affect an experiment. And these may be factors that we're familiar with. These may be factors that we are unfamiliar with. So one type of variable is called a controlled variable. So these are variables that remain constant throughout all of our trials. So for example, if I'm testing the hypothesis that my battery was low on charge, okay, and would I want to also, if I wanted to test that hypothesis, would I also want to, if I changed the starter and filled my gas tank and replaced the wiring to the ignition wiring and I had a charger on my battery, would that allow me to test whether my battery was the problem? No. So when we do an experiment, we want to keep as many variables constant as possible. So I want to leave my car just the way it is. In this case, I'm going to put a charger on my battery before I try to start it again. So I'm testing that one variable. Maybe if that doesn't work, maybe I try the starter. So maybe I have the starter changed. Okay, and I test that idea. Okay, I'm not really a mechanic, so maybe you're thinking, maybe if you know more about cars, you're saying, well, that's a stupid way to go about it. Yeah, I am naive about how cars, the finer details of car mechanics. That's okay. So the reason that we do controlled variables is this is then going to allow us to compare either between experimental groups or to test that one variable, that controlled variable. The one variable that we are testing, that we keep changing, is the independent variable. That's the variable that's being altered in an experiment. So if I'm testing the hypothesis that my battery was low on power, I hook it up to a charger. The independent variable is the power supply to the battery. Okay. So that is the independent variable, is what the investigator is altering. That's kind of an easy way to keep this in mind. Independent, the investigator is altering. In response, we have the dependent variable. Now the dependent variable is actually any variable that responds to the independent variable. So for example, dependent variables, if it is indeed the problem that my battery was out of power, there would be multiple dependent variables that would respond to that. So for example, when I put my key into the ignition, the dash panel lights would go on. Those would be dependent variables. And then when I turn the ignition, my car would turn over and hopefully start. Those would be dependent variables. So a dependent variable is also typically what we are measuring in an experiment. In this case, our main measurement was, did my car start or did it not? Okay. So keep in mind the dependent variable is typically what we are measuring. Now, in addition to independent and dependent variables, we also have uncontrolled variables. And this is really the problematic one. This is any variable when we're doing an experiment that's either not controlled or not measured. Okay, so we're not measuring it, we're not controlling it, so we're not deliberately keeping it constant, we're not measuring it, we're collecting data on it, so or we're not altering it. So these can actually lead to variances. And these uncontrolled variables certainly could affect the results in our experiment. So if I'm testing the charge on the battery and to see if that's the issue, I might not check to see if all the wiring is remaining intact in my car's engine. In fact, there may be a mouse in there that's been chewing on some of the wires, and maybe since it stopped chewing, maybe those wires are intact, so it starts one time. Maybe it didn't start because of the battery, maybe it's just because those wires happen to be intact at that moment. So it's important for us to keep in mind that uncontrolled variables can affect our results of our experiment. And there are always uncontrolled variables since we don't keep track of all aspects of time, space, and so forth. The amount of light, the relative humidity of the conditions, what have you. So there are always going to be uncontrolled variables. Some of those uncontrolled variables are very blatant, typically not. Some of those are very, we don't really notice. So like the mouse that set up a nest in my car as I've been working out of home for so long. So it's always important for us to realize that there are uncontrolled variables, and it is because of uncontrolled variables that we can't use the word proven, because those also could affect the results of our experiments. Now, let's take a look at an example here. Let's say we did a study to determine the growth of the rates of the growth rates of nightcrawler worms grown in 3 different types of soil. So we collected 20 worms. They were placed in 2 meter by 2 meter by 2 meter chambers filled with soil, and the worms were measured weekly over a period of 5 months. And we wanted to see which type of soil they grew the fastest in. So maybe one was a sand, maybe one was a clay, and maybe one was a manure type soil. So we've got those 3 different types of soils. Now, when we explore this, so what would be a controlled variable in this example? So what is the variable that is controlled? Well, we've got a couple of cases of examples of controlled variables. We are going to, the size of the chamber was controlled, that was consistent, 2 meter by 2 meters by 2 meters. The number of worms that we start off with was controlled. The time period was controlled, so those would be controlled variables. Now, the independent variable, okay, that's what we're testing here, that's what we're changing, are going to be the three different types of soils. So we've got three different types of soils. That's our independent variable. Our dependent variable will be their growth rates. So the growth will be the dependent variable, how we measure these worms. Last thing we might take a look at are, what about the uncontrolled variables? So in this case, left a lot of those options open here. Maybe you're looking at, man, this is a really lousy experiment, and that's okay. Hopefully you can see some of those problems with the uncontrolled variables. So what were the ages of the worms to begin with? Maybe one group had a bunch of younger worms. One of the types of soils had a different type of worms, or different age of worms. Maybe we just mentioned worms, realize they're different species of worms. Maybe each of these types of soils had different mixes of species of worms, and thus that affected our results. Maybe the soils were kept at different moisture levels. Maybe one type of soil had a higher relative moisture than another type of soil, and that affected our results. Maybe the amount of air supply maybe the temperature. Maybe these soils were kept at different temperatures due to their locations. So all of these uncontrolled variables certainly could have affected our results. So keep in mind we've got the controlled variables that remain constant. We have the independent variable, that's what we're changing. The dependent variable, that's what we're measuring. And then uncontrolled variables, which is really the devil in the details. Now, as we proceed through, we want to talk about some additional terminology. We talked about hypotheses. Let's just talk about a few other things here as we look to wrap this up. One of these are scientific facts. When we talk about facts, these are repeatedly confirmed observations, things that we've tested over and over again, and we accept them to be true. So, one thing to think about are, do facts change? And this is kind of a tricky one. And that's one of the things we have to deal with. Again, all of our conclusions in science are tentative, and facts can potentially change pending new information. So one example that I can present to you, back when I was a kid and we were looking at our good friend T-Rex here, we saw T-Rex was a nice scaly lizard, and it walked in this upright position just kind of like we do. And so that's the way T-Rex looked like, and it was accepted as a fact that that's how T-Rex would have walked when I was a kid. Now, as we've learned more about the muscular or the skeletal structure of T-Rex and how the muscles would fit, we've learned that, T-Rex really would have moved more like this in terms of being bipedal, much more of a prone type position rather than being this vertical type structure. We also have evidence that during their lifetime, T-Rex would have had feathers on their body. So that certainly is a game changer. So we accept that many of these dinosaurs, raptor-type dinosaurs, would have had feathers during their lifetime. So that certainly is quite a change there. So we have to realize that facts, even though we accept them as truths, they are subject to change pending new information. Now, when we talk about scientific laws, these are descriptions of natural phenomena. Now, one of the things that I want you to keep in mind is the description the same thing as an explanation. This is going to be a very important concept for us coming up here. And I want you to appreciate that descriptions are describing what something is like or how it behaves, explanations tell us why something is the way that it is. Okay? Now, scientific laws are typically easy to identify because they're usually expressed as mathematic equations. So, for example, we might take a look at E equals mc squared. Okay? This is describing the interaction between energy and matter and how they can be converted between one another. So that would be the example of a scientific law. Or we might take a look at the law of gravity. The force of gravity is equal to the gravitational constant multiplied by the product of the masses of the two objects involved and the radius, square the radius between them. So using the law of gravity, we could determine the gravitational attraction between you and any other object in the known universe as long as we know your relative masses and the distance between you. So these are scientific laws. In biology, we don't have very many laws. That's because we have so many variables involved that we don't, laws typically don't come into play. The last term that I want to get into is scientific theory. And scientific theory is commonly used amongst the public as a guess. Okay? And this t-shirt up here is wonderful. It says, "My friends keep saying theory when they should be saying hypothesis." All right. So oftentimes people will say, well, I've got a theory about, or one of my friends might say, I've got a theory about why the lions are so terrible. It's like, no, you don't. You've really got a hypothesis there. All right. Yeah, this kind of sums it up beautiful from the Princess Bride. You keep using that word. I do not think it means what you think it means. So when we think about the word theory, all right, realize it's not the same. A scientific theory is not the same as the common use of the word theory. And that scientific theories are explanations for natural phenomena. These are broad in scope. So this is going to explain why things are the way that they are. This is really our best explanation for how the natural world works. So as we take a look at theories, we have some theories. We might take a look at the example of cell theory, that all living things are composed of cells. Okay? So it's going to describe the structure of things. Okay? Now, as we go into other areas of science, we've got other, say, atomic theory. So atomic theory explains to us that all matter is composed of atoms. So when we find some object, we presume that it is composed of atoms. And not only does that help us to explain the natural world in terms that it's composed of atoms, but realize those atoms have different structures, different characteristics. And this also explains why atoms bond together to produce molecules that produce various substances and explain how those substances behave. So theories explain to us why the world is the way that it is. Now we have to appreciate that not all theories are created equal. Some theories have more support than others. All right? So we'll come back and talk about that in a moment here. Scientific theories are supported by facts, laws, and tested hypotheses. So when we're talking in science that something is a supported theory, that is, it has been tested and is supported. Now, one of my pet peeves is that oftentimes, even when watching a nature show, say something on the Science Channel, and they're interviewing a scientist, they might say, well, I've got a theory about this. And oftentimes, they really just have a hypothesis that it's not fully tested. All right? So, again, theories are going to make predictions. They're going to propose new hypotheses. They have been repeatedly confirmed, and again, are our best explanation for why the world is the way that it is. So we have theories such as atomic theory, that atoms are the basic building blocks in the universe, the basic building blocks of matter. This has been repeatedly tested and confirmed. We don't really question that. Another theory that we might take a look at, evolutionary theory. We really don't question evolutionary theory in the realm of biology any longer. It has been independently tested by major lines of science such as geology, chemistry, biochemistry, physics, have independently tested the theory of evolution. It's never been rejected. Therefore, that is our best explanation for how the diversity of life came to be. Now, you may hear that, there are controversies about evolution among scientists. These controversies, if you will, may be about minor details about the theory of evolution. But the big picture, we certainly accept without much question. On the other hand, we have other theories that aren't as well grounded. So, for example, gravity. Now, gravity is an interesting one. Well, we don't question that gravity exists, but on the other hand, why does gravity exist? That's a really interesting question, and one that we don't fully have a full grasp of. We know that gravity is related to acceleration, probably related to the curvature, the warping of space due to mass of objects. And certainly we don't have a fully mature theory to explain why gravity exists. Another theory that is not as well grounded is the origin of life. How did life get started? So this is the theory of abiogenesis, and that's a theory that we don't have as well grounded because we don't have a lot of evidence or fossils from the very first life forms. So not all theories are created equal. In talking about a theory, one of the common ideas is that if we start out with a hypothesis, we test it over and over again, it may become a fact, and if we test it over and over again, maybe that'll become a theory, or maybe the idea that hypothesis becomes a theory, and if we test it over and over again, it becomes a fact, and then it may eventually become a law. What I want you to appreciate is that this idea that a hypothesis graduates into becoming a theory, which then graduates into becoming a law, is not correct. Okay? This is not how science works. Hypothesis, theories, and laws are separate entities. Okay? These aren't even like apples, oranges, and potatoes. These are like apples, dogs, and raindrops. Okay? These are different things. Okay? So realize a hypothesis, again, is an explanation for a single observation. Theories are broad, overarching explanations. Laws aren't even explanations at all. These are descriptions. So this is not how science works. Okay? I think a better description of how these terms fit together is really best described as like a three-legged stool or three-legged chair. So we have the overarching theory, which explains why the facts are that explain why the laws are the way that they are. The theory is going to propose new hypotheses, which then can be tested and supported. Now, if we think about a three-legged stool, if we pull one of the legs out, say we test a hypothesis and it is rejected, it doesn't hold up that theory, if we pull out one of these legs from the three-legged stool, what happens to our theory at that point? It falls over. So realize that a theory is supported by facts, it must be supported by laws and tested hypotheses. So one of these does not graduate into the other. These are indeed separate entities. Last concept that I do want to touch on here today, and then we'll wrap things up, is the idea of correlation and causation. Now, when we talk about correlation, this is the idea that we have two factors that are related to one another. Now, the question then is, if two factors are related to one another, does that mean that one causes the other? Okay. In a poll done of the American populace, 64% of Americans said yes, that is indeed the case. And I can tell you that 64% of Americans are wrong. Okay? Just because two factors are correlated does not mean that one of those factors caused the other. So we have to be very careful about how we interpret information that we're getting and information on graphs. So for example, here we have some data following the use of Internet Explorer as a percent of market share versus murder rates in the United States. The green bars represent Internet Explorer market share from 2006 to 2011, shown by percentage. Here we've got murders in the United States, and we see that there is a distinct correlation between these two factors. So, if we do not think critically, we might come to the jump conclusion that, oh my gosh, Internet Explorer has been causing murders in the United States. If we only get rid of Internet Explorer, we will prevent all murders in the United States. Obviously not the case. Okay. So hopefully we did not jump to that. You may feel sometimes that that's the case. Well, of course we've got Edge now, so that's a whole other thing. But what I want you to appreciate is that yes, we have a clear correlation between these two factors, but that does not mean that one is causing the other. And that's again why we always have to think critically about the information that's being presented to us. Because many times there are groups out there that want to present factful information like we have here. These are facts, and try to lead you to the wrong conclusions. And that's why we need to be critical thinkers. We need to think very carefully about the information that's being presented to us and evaluate that information. So keep that in mind in terms of correlation and causation. Here we've got an example. So does high stress cause colds? Okay. Well, let's think about this here. Are there possible other explanations for this? Well, if you have other illnesses, that can cause high stress. If you have some other underlying illness, but that other illness may also predispose you to a cold. Or maybe you've got a poor diet. You're not eating well. We know that eating poorly can lead to stress, but eating poorly can also cause colds. Lack of exercise. Okay, if you have if you don't exercise, that can increase your stress levels, or could lead to higher stress levels, and also lead to a weakened immune system. Similarly, if you are not getting sufficient sleep, that will contribute to higher stress levels. That certainly will weaken the immune system. So it's not necessarily, the conclusion cannot necessarily be drawn that high stress causes the colds. There could be underlying factors. Certainly, could we draw a correlation between stress and colds? Certainly, we can draw a correlation there, but realize that we have to think about other factors that are involved and not simply look at the obvious correlation. Think about What are those other uncontrolled variables, if you will, that could be affecting the correlation between these two factors? So that wraps up our basic discussion on the nature of science. If you have questions about what we've discussed here today, please join in with the live sessions or contact me by email or chat, and I'd love to discuss that with you. So until next time, have a great day. Goodbye.